Hello everyone, my name is Nityananda Guhai. I've been working with SigNoz for the past 3 years, building on top of ClickHouse and OpenTelemetry. So I'll pass it to Srikant to introduce himself.
I was one of the maintainers for OpenTelemetry Python. I still part of OpenTelemetry agent management, where I'm one of the core team members. In this session, we will go over some of the so SigNoz has been an open source project for a long, and in this session we operating both ClickHouse and OpenTelemetry. Over the years, we have learned a lot of insights into operating them at scale. In this session, we will be focusing on specific about SigNoz. SigNoz is ClickHouse powered. We extensively use ClickHouse. It's an open source project with 220K stars on GitHub and built for OpenTelemetry, operating at a scale. Yeah, so over the years, we have been operating ClickHouse and OpenTelemetry at scale. There are a lot of interesting things to talk about. We use different merge tree engines. We have custom settings. We have batching inserts, and then there a lot of things we have learned. But it will be too much to discuss detail. But in this session, we will be discussing about the schema, because the performance of your queries largely depends on the schema how you design. And then in this session, we will be focusing just the schema part of the how we done it.
So let's start with what are the indexes with ClickHouse. So right now we have like two kinds of indexes that are present for ClickHouse. One is the primary index and the other one is the secondary index. Let's go through each of them so that we can get an idea what each of them are. So with the primary index, what it allows you to do is basically skip data based on granules. So the index is on granules rather than on individual rows. What it allows you to do is skip the entire granule if you want. So in this case, I have an example where there are 3 columns in my table, and I've basically sorted the data by 3 tables, and the primary key is user ID and URL. And for each granule, what I'm doing here is basically the primary index stores the first row of each granule. So here, this row is stored in the primary index, and this row is stored in the primary index. So that's how the primary index of ClickHouse looks like. Let's go to the next slide where we talk about the secondary index, that is skip index. So once you have the primary index, what you want to do is basically, let's say there are some more columns where you want to filter on. For improving those queries, you will have to introduce another indexes, that is the skip indexes. But what skip indexes allow you to do is tell whether certain data is present in a granule or not. So if it's not present, skip index will allow you to skip that granule entirely. So this is what skip indexes helps you with. So let's start with the first version of our log schema. So this is the first version of the log schema look like. So here we had the basic columns that we have, the timestamp, ID, body, and some different attributes that we have, service name. And this is our order by. So here we are ordering by timestamp, ID. Now here our data is ordered by timestamp, ID. And the primary key is also timestamp, ID. What it means is all our data that is stored in the granules are ordered by their timestamp and then by their ID. Now this was a good initial version for us because it allowed us to do all sort of queries with the range of timestamp. And then any kind of filters that we wanted to do on other attributes, what it did was we just introduced a new skip index. So let's say I'm trying to filter on some service name. What I will do is I will add a skip index, and that's how we managed our first version. But within a few months, we realized that this is not good enough. The skip indexes are like you cannot predict how they will work for different attributes. A lot of users, they have different kind of skip attributes, and creating skip indexes on them doesn't actually improve the performance until unless you know what the data is. So you have to create them very precisely. Now what we did was to overcome that problem, we saw that some users were querying some attributes very frequently. So what we did was we went with projections. What projection basically is that, so once your data is stored in the table, it is ordered by certain columns. Now let's say you want to improve the performance of some other columns. What you'll do is you'll store the data once again, but this time it will be ordered by something else. So in this case, I wanted to improve the performance of these 4 attributes. So what I did was I created a projection on top of the main table. Now my data is duplicated with this order by, and this is the primary key for that order by. But again, this is also a problem because the demands of the user vary from one to another. And we cannot basically keep modifying the projections over time. Some of the issues with projection are that it occupies storage twice, and the other one is that you cannot actually remove some columns from a projection. And one more issue we faced was, let's say I added a column to a projection. What happens is I cannot actually rename the column. So once you add a column to a projection, you can never rename it until unless you delete the projection and then rewrite it again. Yeah, and one more issue we faced was, let's say you have projections in your table, but ClickHouse may not actually choose the right projection that you want. So in some case, you might want to choose some projection, but you cannot actually say ClickHouse to do it, or it's actually very difficult to do it. So while we are doing this, we also observe like what are the type of queries that users are running on. So I've seen that the kind of queries that user runs on is basically they will always have some filters, and they will always have some resource filters. Example, they will say, okay, uh, I have some logs coming from this source, that is Kubernetes pods, and I want to filter on that. Or I have some logs coming from ECS CloudWatch, and I want to filter on them. So those were the common patterns that we see. And then one more thing that we saw was, since we ordered our data by timestamp, ID, our data actually was spread over granules. So let's say some data is coming from Kubernetes, while some data is coming from ECS. What happens is, in the same granule, the data is spread over. So skip indexes were not performing well. So now we wanted a system where basically without changing the order by key, we wanted to build a schema in such a way that it will always group the data of the same resource together. So by this, what we wanted to achieve was, okay, let's say data from this source, two sources are coming. We wanted to make sure the sources are clubbed together so that we can utilize the primary index better. So here comes the hierarchical resource fingerprinting. So this is something that we came up with. So here is an example that I will go with. So here, let's say we have some logs coming from different sources. So here the first log is coming from cluster C1 and namespace N1 and the pod P1. Second is coming from some CloudWatch log stream. And the third is also coming from the same first cluster and the pod P1. And like this, logs are coming from different clusters. Now, how do we make sure that C1, N1, and P1, all the logs from those cluster, that resource is clubbed together? So first, we'll have to create a fingerprint that is based on hierarchy. So in this case, we have created a hierarchical fingerprints. So in this case, for all the Kubernetes pods, we have made sure that the cluster comes as the first item in the fingerprint, namespace comes in the second, and pod comes in the third. And then we hash the entire thing and put it in the fingerprint as well. So you can see for the logs coming from P1 and P2, so the fingerprints are same. That's the first and the third one. Now let's see, once we have this fingerprint, how ClickHouse will actually order the data. So here you can see this is the actual data that will be returned to ClickHouse. Now we have sent data which is not ordered, but here you can see for the same cluster, for the same instance, for the same pod, it will be clubbed together. For the same cluster, for the same instance, for different pod, it will be nearer to that. And for the same cluster, for different namespace, it will be below that. So that's how we basically model our resource fingerprinting in such a way that we don't need to modify the primary key, and then we can basically update our hierarchy to make sure that we support clubbing of data from different sources. Yes, and this is what the final order by look like. So what we did was, for a bucket, let's say 1 hour or 30 minutes, I will store my data in such a way that for 30 minutes interval, all my logs from one source will be clubbed together, all my logs from other source will be clubbed together. So this way, you can actually skip a lot of granules and then improve your query performance for resource attributes. Yeah, so let's see what are the performance difference that we notice. So this is the example query that I wanted to show. So here what it is doing is counting the number of logs per minute and adding a resource filter that is namespace name equal to dev. This is run over the entire data of the table. Now let's see what was the performance that I noticed in the first schema. So here you can see this thing doesn't help because we are querying the data over the entire table. Now here comes the skip index. It couldn't do anything because our data is spread across all the granules. So it just skipped 1 or 2 granules, but I think it was not successful. So let's go to new. So in this new schema, same till here, we cannot skip any granules because we were querying over the entire data. And here comes the resource fingerprint. You can see we came from 41,000 to almost 222. This is the magnitude of improvement in our query performance based on the resource fingerprint. So right now, what you can do is you can query on any resource attribute in our system, and your query will be much faster without doing anything. So out of the box, we provide very high performance on the resource filtering. And then what this achieved us is basically resource users for a ClickHouse, because now you don't need to write to multiple projections, and also disk users because data is not replicated. We almost saw thrice x storage savings in our traces and twice x in log.
So my colleague Nitya explained how we evolved for the logs and traces. You could like now I'll be talking about the metrics. You could ask how is it different from the logs and traces? Do you need to do like what we learned with the experimenting this? So metrics differ with the logs and traces in by nature that they usually have a very consistent labels or dimensions or attributes, whatever you may refer, and they're expected to be faster and to be retained with high storage efficiency. So before we jump into that, let's briefly look at what does the metric data model look like when it is coming from the any sources. Here there are two parts to it, the sample and the time series. Here you can see in this image there is a metric name, there are certain labels, and then the timestamp and the video. So the timestamp and the value is referred to as a sample. The metric name and the labels combined is usually referred to as a series. So usually any metric has like the labels and the values that go into are usually controlled. They are very consistent. You just don't put random things into it. And the metric usually metric has a limited number of time series associated with it. Now let's just say we want to model this as a ClickHouse table, right? Like one way to go about is to like use the same thing that we did for the logs and traces, just use the single table. And the other way to, we did that, and then we did the performance, like we did the experimentation to understand how does it do. Like if I ask any arbitrary question that give me any metric, there could be custom metric, there could be metrics coming from any sources, we don't know. So we wanted to build a platform where we do not know anything about anything beforehand. Like if we know things about the beforehand, you can always optimize it for, okay, so let's just say you have a known set of metrics, known set of things that the people ask for, you can build it very efficiently. But with the SigNoz, like we want it to be that we want to build a platform that generally applies to anybody without any restrictions. So we had two options to go with. Like one is single table approach that we have for the logs and traces, other is two tables approach. So we will discuss about what we learned with the single table approach and the two tables approach. So if we were to model the data model that we discussed into a single table approach, this is how it looks like. So there's a metric name, there's a fingerprint, which is also a hash of it, and there's a timestamp and the value, the labels. Here you can see the labels is of a map type. So when you get the data from like different sources, you don't like such. Let's just say one of open source users is using it primarily for the AWS. We don't know all the attributes that come beforehand. Let's just say they are sending some custom attributes. We do not know anything beforehand. So while the data is consistent, but you never know what are the attributes that they have beforehand. So you need to have a certain data type that can handle attributes, dynamic attributes. And ClickHouse has number of options to provide. So you could JSON serialize it, store it as a string, or you could use pairwise arrays. So where you do the attribute value and mapping, and you could use maps. So with the option that you have, JSON serialization, it's CPU intensive. Pairwise arrays, they don't support the indexing. So one of the options is to use labels as a map of string to string. Now this is where you could say you could build you could ask for any arbitrary question but still get the questions. Now what are the issues with the single table? So the issue with the single table is that anytime, let us say you have a custom metric and you are asking for I have my payments processed, and then give me the total payments processed by some example, let's just say instance ID. Now the problem with us is that because you do not have a direct column created on top of it, you end up accessing it from the map. Now when you start accessing anything from the map, ClickHouse, although it's a map, it's usually underlying it maintains a tuple. So anytime you access anything from map, it unpacks the whole object and reads entire thing even though you just accessed one attribute. Now imagine doing this without any resource filtering. So my colleague talked about resource filtering, right? Metrics, the nature of that is that now give me the pod CPU usage across entire cluster, like I'm running 100 clusters, give me the pod usage across all pods and give me the top 10 attributes. So the worst case in metrics is that you don't have any filtering. You are just going to run it on entire data. Now imagine trying to unpack the labels object for hundreds of billions of rows. It was extremely slower, not that because ClickHouse is slower, because ClickHouse ends up unpacking lots of maps and then reading unnecessary data. So because your query is only as fast as the amount of data it is reading. So the lesser the data you read, the faster query. So because we cannot predict these attributes that they are going to access beforehand, it ends up being extremely slower. And then the other thing about this is that the storage efficiency. You want to retain metrics for longer, you want it to be cheaper, but repeating the labels for every sample, like every sample on its own is just a two numbers, timestamp and value. Now if we repeat the labels, which is around, like let's just say on average 2 KB, you end up repeating the 2 KB for billions of rows, which means that it will take more storage. So this was the issues that we have seen with the single table approach. Now, can you do something about the single table approach to make the things better? From the storage side, you can't avoid it. Like you can't remove the labels from the single tables. So the storage wise, you don't have any gains. Now, we try to, and the one option is to use materialization. So let's just say, observe the system over time, look at their query patterns, materialize it. Next time when they access the same label, you are going to use it from the materialized column rather than using it from the labels map. So it reduces. But the problem with this is that doing it, it brings a lot of operational challenges. For example, you are continuously ingesting the data. Materialization and the dematerialization you have to handle with care. If you don't handle with care, let's say you dematerialize something and then the inserts are happening. If you remove the column without care, the inserts will start to fail because insert statement had a column, but you removed it. So it brings a operational complexities. Now at the time when we were building this, there was an object JSON that ClickHouse folks have talked about. So we tried with it, but we didn't go with it because it had its own challenges and it was experimental. And then we tried to experiment with the two tables approach. In the two tables approach, if you see, we separated it into two tables. One is samples and the other is time series. In the samples, if you just see, these two things are the important ones. This is the timestamp, this is the value, so that's just the sample. In the time series model, you have the labels, which is JSON serialized string, maps are JSON serialized strings. Now if you see, now with this approach, what happens is that this table will just have the samples, this table will just have the time series. So anytime you want to get any result, the problem with this approach is that anytime you want to get a result, you have to join these tables, right? So, however, how did it compare it to the single table approach in terms of query performance and the storage? In terms of query performance, even though we are using the join, the ClickHouse is not known for joins. But however, matrix has a certain nature to it. The right side of the table, it's usually going to be smaller, like you know. So take any metric name, you know that maybe a 10 million time series for a metric name, right? Like you're always going to have a certain known number of time series that will be there for a metric. Now because of the nature of the metric data, the right side of the join is always going to be slower. So in a general case, so with this table approach, what it ends up happening is that in general case, without having to worry about all the object JSON and then the dematerialization operational complexities, in all the cases, except when you create a materialized column and then highly optimize it, in all cases, this two table approach has shown the better query results. And then in terms of the storage, now you can see there is no labels anymore here. So we're not repeating, labels is no longer redundant here. And then the storage efficiency also, it's highly efficient. Yeah, next thing, we have seen the join. Now, even when you are using the join, even when the right side is slow, right side is not a big table, we still, like, people retain for 6 months, 2 years, right? So to improve the performance of such queries, what we do is we use the materialized view. So we pre-aggregate data at 30 minutes, 2 hours, 1 day, so that when you ask for longer queries, we use these pre-aggregated tables for the range queries that are beyond the few days. Yeah. So is ClickHouse the best for the metrics? Not yet. So at this point, it's not the best. If I have to say that So there are few things we are looking forward to with the two tables approach that we have. If you recall, the two tables have the same order by key. Now, when you have the same order by key, when you have join, there are a class of join algorithms where if you have the same order by key, you can efficiently do it much faster. But ClickHouse doesn't have support for that real merge join support. So with the two table things, what we are looking forward to is to get the merge join support enabled, and then do the experimentation again to see how it improves it. The other thing that we want to try out is the new JSON data type that ClickHouse folks have talked about. That okay, now I will go back to the single table, even though it may be storage. We don't know how efficient the new JSON data type in terms of storage. We'll go back to that. We'll experiment. So these are the two things that we are looking forward to in terms of how do we model our metric steps. Cool. Yeah, that was about it. Thanks everyone. We are growing. We are hiring, processing, ingesting data at tens of billions of entries every minute. Come work with us.